Thank you for the lovely introduction, and thank you all for taking the time to be here this afternoon. If you take a look outside at the exhibition booths and in some of the previous presentations, we have seen a recurring theme that going green, reducing fuel consumption and reducing emissions is of utmost importance. And that is where power takeoff units come into play. Power takeoff units, or so-called PTOs, are an efficient way to produce electrical energy on board. However, integrating a PTO has a significant effect on the torsional vibration system. And it was after realizing this impact that my co-authors, Mr. David Richter-Trummer and Andreas Thalhammer, and I decided to investigate and take a closer look at the torsional vibration aspects of different power takeoff units for two-stroke marine propulsion systems. So a quick overview. I'll start off with the motivation, which is how electrical energy, fuel efficiency, and torsional vibrations are all linked. I'll then move on to electrical energy production, which is the differences between generator sets and main engines with power takeoff units. Then I'll move on to the working principles of how each type of power takeoff unit operates. And then lastly, we look at the vibratory aspects, which is the response of each type of power takeoff unit. And those last 2 points will be repeated for each type of PTO. And in this case, we'll only look at the three major ones, which is the inline shaft generator, the tunnel gearbox driven generator, and the front end shaft generator. So the motivation, as I said, for electrical energy production on board is not just a secondary function, it is critical for the safe operation of the ship. So think in terms of your lights, your navigation systems, your communication, your heating, ventilation, air conditioning, as well as any type of pumping is run off electrical energy. And thus it makes sense to produce that as efficiently as possible. And that's where power takeoff units come into play, because they extract electrical energy from the main engines, which reduce the number of generator sets required. So in terms of fuel efficiency, implementing these PTOs increases fuel efficiency, which directly lowers fuel consumption, which lowers operating costs, reduces exhaust emissions, and ensures better compliance with environmental legislation. To put that into numbers, if you consider a medium to large container vessel that's burning about 100 tons of fuel per day, a mere 1% increase in fuel efficiency saves you a ton of fuel per day. It's not all positives though, it has some challenges, and that is in terms of the torsional vibration aspects, where each type of PTO unit changes the torsional vibration system, and regardless of which unit you use, it increases the power demand of the main engine, which also increases the vibratory torque and places additional stresses on components along the powertrain. All right, so here we have the two main types of engines on board. On the left-hand side, we can see the generator sets, or so-called gen sets, which are typically 4-stroke. And on the right, we have the main engine, abbreviated ME, which is typically 2-stroke. And if we look at the primary function of the generator sets, that is electrical power generation, whereas for the main engine, the primary function is ship propulsion. In terms of the operation for the gen sets, it's typically on demand or continuous, whereas for the main engine, it's typically continuous. So that means that when the ship leaves the port, for 24/7, that main engine is running until it arrives at the next port. In terms of the number of units on board, the gen sets typically have multiple units for load sharing and redundancy. In case one unit fails, others can kick in and take up the load of the failed unit. For the main engine, it's typically single or twin engine configurations. And just here, important to note is the power capacity of the main engine is typically in the order of magnitude 5 to 7 times greater than the gen sets. All right, so now we're getting into the more details of the PTOs. As I mentioned earlier, they extract mechanical power from the main engine and convert it to electrical power. And in our daily business, we've seen a rising demand for fuel efficiency. And because these are fuel efficient, they have seen increased implementation. So on the top right, we can see the inline shaft generator that has the highest power output. On the bottom left, we can see the tunnel gearbox driven generator that's considered a medium power output. And right at the bottom right on the end there, That's your front end shaft generator, which also has the lowest power output. So the selection criteria is that the type of power takeoff unit chosen depends primarily on the vessel size, the main engine power, and whether it is a new build or retrofit. And regardless of the PTO type, the power demand of the main engine is increased, so we see an increase in vibratory torque. And each type of PTO uniquely changes the system inertia and stiffness, which results in a frequency and amplitude shift. And lastly, there's some power takeoff units can work in reverse, which means they can operate as power take-ins, which is where they provide power to the propulsion line, and power take home, which is in case of emergency, the generator can run and turn the propeller and operate or provide the ship safe passage home. So in terms of the actual operating principles of a PTO, they use Faraday's law of electromagnetic induction, which is the induced voltage E, which is directly proportional to the product of the number of turns in the coil, denoted by N, and multiplied by the magnetic field strength B, as well as the coil area A and the rotor speed omega. So what does that mean for us? It's the relationship between generator size and rotor speed. So assuming that the number of turns in the coil N and the magnetic field strength B are kept constant, then we can say that the induced voltage is directly proportional to the coil area and the rotor speed. So by increasing the rotor speed, we can reduce the coil area and still generate the same voltage. And most critically for us, that means we can reduce the physical size of the generator by increasing that rotor speed. So that brings me to the first type of generator, which is the inline shaft generator. And that is attached directly to the shaft line, where we can see here. If it weren't there, that intermediate shaft would be solid all the way through. And now obviously with the addition of the generator, we have a large rotor here that's considered torsionally rigid, which effectively shortens the shaft and increases the shaft stiffness. And as the previous point was that increase in rotor speed lets us use smaller generators. Unfortunately, this design has no gear reduction, so we cannot use smaller generators. And that also contributes to that shaft line inertia and stiffness increasing. However, it's not all negatives. It has some very good pros, and that is that they're straightforward and robust design requiring minimal maintenance. And this type of generator has the highest power output. All right, so let's look at the results. So this is the first case, which is a standard case. And we can see the text there says increased main engine power demand, and it can be upwards of 20%. In this particular case, it's torque limited. So if we look in terms of the engine power curve image here, we have engine power on the left and engine speed and RPM on the right. And that turquoise block or that column denotes the part where the PTO is operating or active. The gray curve is PTO off, which means it's turned off, not extracting any power from the main engine. Gray curve there. And the PTO on, it's turned on, it's extracting power. So what does that mean for us in terms of torsional vibrations? It means that increased power demand results in increased vibratory torque. And that can be seen there on the steel spring damper vibratory torque on the right. In the same step up here is mimicked in terms of the vibratory torque over here. Then the same can be seen for what's seen for the steel spring damper can be seen for the crankshaft, where we compare the crankshaft vibratory stress to the engine speed, and that same step can be seen there again. And that's all due to that increased main engine power demand, which increases the vibratory torque in that region. And then most interestingly for this case was, however, that increase in vibratory torque caused the IX M86 limit to be exceeded in the screw shaft, which meant that this damper could not have been recommended for this. So there are 3 ways we can solve this issue. So that's just to make sure everyone sees there that blue curve has reached or exceeded the limit there on the red. So to increase the limit, we can increase the tensile strength of the material. That's the first option, however, that's quite expensive. The second option would be to increase the size of the shaft. However, that also has implications further along, that it changes the frequency and amplitude of the first resonance peak. And the third option would be to decrease the load of the PTO. That would also reduce that peak over there. The second type of case for the inline shaft generator is the retrofit case, where we see again here the increased main engine power demand, upwards of 20%. However, in this case, the gray curve denotes a system where the PTO was not on the ship. So this was a ship that existed before. It ran for however many years, and the customer said, no, they would like to put a inline shaft generator in as a retrofit case. So that means you take the intermediate shaft, you split it up into two smaller generator shafts, and you have that rotor in between. So, well, as I've said, and that is the effect that it has on the steel spring damper vibratory torque, as well as other components along the shaft line, in that it increases that peak and it shifts the peak to the right. And however, in this case, it wasn't all bad. The steel spring damper, the crankshaft, and the shaft line all had enough safety margin to absorb the increase in vibratory torque, and this damper was able to be recommended. So that can be seen there on the crankshaft. It's all beneath the limit, as well as for the screw shaft. We move on to the second type of generator, which is the tunnel gearbox driven generator. It is now attached to the shaft line via a highly flexible elastomer coupling. We can see here first is the gearbox, and then the generator attached over here. And this can benefit from that gear reduction, so it has a increased rotor speed, which means that the shaft line can remain lightweight and flexible, and higher rotor speed means that smaller generators can be used. And as mentioned before, this is the medium power output case. So let's look at the results. So for the tunnel gearbox driven generator, it has an increased engine power demand. Again, every single type of generator has that. And in this case, it's upwards of 25%. Can be seen again. The gray curve now is PTO off, which means that it's a system where the PTO is attached to the system. However, it is not drawing any power. And the blue curve is a PTO turned on, extracting that mechanical power. So here we have here on the top right, the elastomer coupling thermal load, which compares the thermal load in kilowatts to the engine speed. And we can see here, this is all now for this PTO on case. So that's all the curves are blue as well. The ideal firing is a solid blue curve at the bottom here. And we can see that during ideal firing, it's not really an issue. However, for unbalanced firing, which is denoted by the dotted and lined curve here, as well as misfiring, the misfiring, unbalanced firing induces low water vibrations in the generator branch. And that can be seen clearly as well in the vibratory torque at the bottom, where the limit is exceeded. And as I mentioned here, in this type of application, the highly flexible elastomer coupling is sensitive to these low water vibrations in terms of continuous thermal load capacity. And as a result, a restrictive bar speed range may need to be implemented to protect the system against excessive vibratory torque. Okay, coming to our last type of generator, which is the front end shaft generator, all the way on the free end over here. And they are attached to the free end via highly flexible steel spring coupling. And it can also benefit from that gear reduction, so the increase in rotor speed compared to the crankshaft speed means, again, smaller or compactor generators can be used. And the biggest pro of this system is that the shaft line remains completely unchanged. And as mentioned there, the compact generators allow for small installation size, particularly if you have limitations towards the bow of the ship. However, they do have the lowest power output. Okay, in terms of the results, so there's increased main engine power demand, and especially there in the low speed range, it can be upwards of about 45%. And this now compares again as the second case, the gray curve, no PTO, so that's a system without a PTO on the system at all. And then the blue curve is a PTO switched on, drawing power as well, obviously attached to the free end. So here, the addition of that highly flexible steel spring coupling and a front end shaft generator has only a minimal impact on the peak resonance. And that can be seen here in the intermediate shaft vibratory stress, that the shift is only slightly to the right. That blue peak compared to the gray peak, the frequency shift is only slightly to the right. And the last point here is that the amplitude of the resonance peak, however, is reduced significantly, and that's due to the high damping properties of the steel spring coupling. And this ensures adequate safety margin during misfiring and unbalanced firing conditions. So we can see here the peak resonance was reduced by that damping of the steel spring coupling. And then as the PTO is engaged in this blue region here, the curves switch. So you can see the gray curve is above the blue curve, and then here the blue curve above the gray curve, as you would expect because of that increased engine power demand. All right, to summarize, the rising demand for fuel efficiency has driven an increase in power takeoff unit integration on two-stroke marine powertrains, and we've noticed that on our daily business as well. And the type of power takeoff unit chosen depends primarily on the vessel size, the main engine power, and whether it is a new build or retrofit. And each type of PTO uniquely affects the torsional vibration system. And lastly, critically for us, is that the special attention is needed when dimensioning torsional vibration dampers and flexible couplings to handle the extra stresses caused by integrating power takeoff units. All right, thank you.